Alrighty, so for the first topic today, we are going to be solving quadratic inequality written in factored form. Our directions are to graph the solution to the following inequality on the number line. The example that we're given is x plus 7 times x minus 1 greater than 0. So how are we going to solve this? We are going to use the steps above. So step 1, we want to rewrite the inequality so that one side is 0 and the coefficient of the leading term is positive, then factor. So and for step 1, we're essentially looking for three things. The first one is to see if one of your sides is equal to 0. And when we look over here, as you can see, the right side is equal to 0. So that's good. The second thing, it would be the coefficient of the leading term is positive, and then thirdly, we would factor. However, in this example, this is already factored. So we don't have to check if the leading term is positive. We don't have to factor. It's done for us. So step 1, done. Right? So step 2 says find the boundary points of the inequality. So we're going to find all values of x that make the product of the inequality true. So how do we do this? What we're going to do is that we are going to set this inequality into an equality. So what do I mean? It's going to be x plus 7 times x minus 1 equal to 0. And then we're going to use the zero product property rule. So what is that? That is x plus 7 is equal to 0, or x minus 1 is equal to 0. Right? When we do that, we get x is equal to negative 7, or x is equal to 1. Right? So our boundary points, okay, these are our boundary points. So what are we going to do with these boundary points? So step 3, we're going to plot the boundary points on the number line. Okay, so let's use a different color. I'll use blue. So we're going to find x is equal to negative 7. It's right here. And then x is equal to 1, which is right here. So it says that it divides the number line into intervals. So what does it mean? So essentially there's like an invisible dotted line. Okay. And then now so these dotted lines now is separated into 3 intervals. So we'll call this interval 1, this is interval 2, and this is interval 3. Okay, and this was step 3. Okay, so what is the fourth step? Now we're going to select a test point from each interval and substitute it to the original inequality. So if the test point makes the original inequality true, then that interval is part of the solution set. So let's pick another color. So now what we're going to do is for each of these intervals, let's pick a test point. So over here, we can pick a number between negative infinity and negative, oh my gosh, this is not negative 7. 1 second, guys, sorry about that. Apparently I don't know how to count. Okay, so negative 7's over here. Okay, so let me redraw this thing. All right, so now our choice is, so we want to pick from negative infinity to negative 7. So you can pick whatever you want. You could pick negative 8, negative 9. I'm going to pick negative 10. Okay. For the second interval, we can pick a number between negative 7 and 1. So for me, I always like to pick 0 if I'm given the option. And then secondly, we want to pick a number between 1 and infinity. So, I don't know. This time, let's go with 3. Okay? It doesn't matter what you pick. So what are we going to do next? We're going to take these test points and we're going to plug it in to our original inequality. So one thing I want to note is I found all the test points first, and then we'll test it. But what you can do is you can test each interval, or you can pick a test point from an interval, and then you can plug it into the inequality right away. Okay? It doesn't matter. The order of that does not matter. So let's test it out. So for step 4, okay, so essentially, step 4, this is like A, and this is like a B, okay? But these are also interchangeable. Well, not interchangeable, but like like you can do each interval separately or just do the whole process as on its own. Right? So what are we going to do? This is x is equal to negative 10. I'm going to plug this into the original inequality. So we have negative 10 plus 7 and then negative 10 minus 1. Is this greater than 0? When we solve for it, we get negative 3. This is negative 11. Is this greater than 0? Okay, when we multiply these together, a negative times a negative is a positive. Okay, so is a positive number greater than 0? Yes, it is. So what does that tell us? That tells us that this is part of our solution. Okay, now we're going to test x is equal to 0. So actually, let me just go down here. So x is equal to 0. Maybe I'll also do it in a different color. Let's do maybe orange. Okay. So I have we have x is equal to 0. So when we put that into the original inequality, we get 0 plus 7 and then 0 minus 1. Is this greater than 0? And then we'll get 7 times negative 1. A negative times a positive is a negative. Okay, so we get negative 7. Is negative 7 greater than 0? No, a negative number is not greater than 0. So what does that mean? That means that this interval is not included. So the last thing we're going to check is when x is equal to 3. Okay, and we're going to plug it into the original inequality. So since I can't see up there, we'll look at it from the right. So we have 3 plus 7, and then 3 minus 1. Is this greater than 0? Then I have 10 times 2. Is this greater than 0? And I have 20 greater than 0. 20 is positive. A positive number is greater than 0. So what does that mean? That means that this interval over here is also included. So now that we picked test points and then we tested those test points, what do we do next? So the last step is we want to test the boundary points in the original inequality. So if the original inequality is strict, do not include the boundary points in the solution set. If the original inequality is defined using like less than or equal to or greater than or equal to, then you want to include the boundary points that are defined, right? But take note, any boundary point that makes an expression within the inequality undefined must always be excluded from the solution set. So if we were dealing with fractions, like the rational numbers, or if we're dealing with radicals or square roots or any type of root, then we would have to test the boundary point. So one note I want to make over here, if it's not continuous, okay, so lucky for us, like a polynomial it's continuous on the whole line. But if we're unsure, when we have this type of situation, so if there's an equal sign, I would always test. Okay, just to be sure, right? So it never hurts to do it. However, for ours, it is strictly greater than. Since it's strictly greater than, I know automatically, without a doubt, that it is not included. So, let's see, I can use light green or something. So what are these? These are actually open circles. Okay, same thing when we were dealing with inequality, the linear inequalities. Open circles represent not included, closed circles represent included. So now I put this in the final step, but step 6, right? So it's invisible. But the last thing you do is you're going to graph your final solution. Okay, so how do we do that? We're technically going to bring this down. So we're going to replot our boundary points, but with open or closed circles. In this case, it's going to be open. Okay, on -7 and 1. And then we're going to color our solution. So what intervals are included? We included the third interval. We didn't include the middle one, so that one stays empty, and then we included the third interval. Okay, so this is our final solution. So now I want to take it a step further, and I want to ask you guys what the interval notation would be. So recalling when we do interval notation, we always go from left to right. So it's colored, there's no stopping from what I see here. So what does that mean? This is interval notation. Okay, so this is going to be negative infinity, and then all the way to -7. Is it going to be a parentheses or a bracket? If you said parentheses, you are correct. It is not included, so it is parentheses. Okay, and then so there's more than one part shaded, right? But they're separate. So how do I combine them? We're going to do the union. Okay, and that includes the second interval. So the first number I see that's included, I didn't graph this right again. So let me redo that. Okay, it's supposed to be at 1, not 3. Just don't know how to count, obviously. All right, so now it's going to start at 1, and again it's a parentheses because it's open circle, and then we're going. It never stops coloring. So, infinity. This is our interval notation. I want to take it one step further, and I want to do the set notation. Okay, so what is the set notation? So, set notation is like what all the x's that we're going to include. So, the set notation, so it's going to be the set of all x such that x. So if we look at here, it's going to go from -7 to infinity. What does that mean? If x is strictly less than -7, or if x is greater than 1. Right? And that's our set notation. So yeah, that's just taking it a step further because it will help for our future examples. So that's the end of section 1. Section 2, we'll cover, we'll still do the same thing. We're just going to look at different cases.